Okay, so the last chapter, chapter 10, is titled Unsupervised Learning, okay? And so unsupervised learning is the kind of, I guess, statistical learning methods where you do not have a target, okay? So all of the other learning methods had a target or response variable. So we either wanted to predict the category or the classification of an observation. So it would be something like, with these inputs, predict if it was a success or a failure, if somebody, so logistic regression, you took numeric inputs and you predicted yes or no. And then with kind of the LDA and QDA and stuff, you took in the numeric inputs and you predicted some kind of classification. Okay, so you had a target or a response variable to predict. With the other methods, such as the linear regression and the additive models like the splines and whatever else we looked at, we had a numeric response. Okay, so we had inputs and we had an output, and we wanted to predict those things as well. Okay, so those were all supervised learning methods. Okay, so you have the input variables, the features, and a response y. Okay, and so with unsupervised learning, the difference here is that there is no response. Okay, we are not interested in prediction because we do not have an associated response variable y. Okay, really, as far as the data goes, you can easily turn a supervised learning thing into unsupervised learning by just changing the letter y to x. Okay, so before it was something like predict the number of wins for the football team, and we said y is the variable that we want to predict. But if you just say, oh, you know what, let's make this an x variable just like every other variable, like the number of yards and the number of rushing attempts or whatever, if you just say this is just another x variable, then suddenly it's an unsupervised learning. If there's nothing to predict, then it's unsupervised, okay? And then if you want to go from unsupervised to supervised, all you have to do is just pick one of the variables and say, you know what, I want to now predict the number of yards, okay? Predict the number of yards. You can set yards to be the y variable, okay? So it's just a matter of picking or not picking a variable to predict, okay? It's not that certain types of, the data that comes in is more unsupervised or more supervised or something. It's the same data. It's just for supervised, you've picked one of the columns and said, this is what we are predicting, okay? And then unsupervised, you're saying, well, I'm not gonna predict this thing, okay? So it's just framing the problem a little bit differently, okay? All right, and so there's a few goals for unsupervised learning. Unsupervised learning is generally trying to discover something. The goal is to discover something interesting about these x, okay? Something interesting, okay? And one question is, is there a way to visualize this, which is always challenging, because oftentimes our data is high dimensional. You might have like 20 columns or 30 columns or something like that, right? I think how many columns are in the football data? Something like 30, something around there, okay? But as far as visualizing stuff, you're only really able to visualize as spatially, maybe 2 or 3 dimensions spatially, and then you might be able to add like another dimension by using color, and another dimension by using like the size of your points or something. And beyond maybe 5 dimensions, it's really hard to visualize because things just get really messy, right? It's difficult. And so if you have 30 dimensions in your variable, how can you project, or how can you visualize, as much of the information possible without, by, reducing it to, ideally probably just 2 or 3 dimensions, okay? So, how can we do that? And so one of the ways we can do that is via principal components analysis. It's an idea of reducing the dimensionality of your data. You've got 30 variables in your football data. How can you visualize this a little bit nicer in 2 or 3 dimensions? What's something that can be done, okay? So that is that's one thing there, okay? And then so the textbook frames principal components analysis as a tool used for data visualization or data pre-processing, and that's true, okay? And then the other kind of unsupervised learning is clustering. A clustering is kind of used to group observations based on some kind of similarity measure, okay? So you're trying to group similar observations together. It's important to note that most of these techniques apply for numeric predictors, okay? If one of your predictors is categorical, it gets a lot harder, okay? Trying to cluster based on a categorical predictor is really hard, because the categorical variable is already kind of clustered, it's already kind of clustered. You can, like, if you're doing something based on gender or something, and to keep it simple, let's just say you're going to do men and women or something like that, okay? If you're going to go with those 2 genders, then it already clusters, right? It already clusters. It puts the men in one and the women in the other or something, okay? Maybe non-binary somewhere else. It already kind of clusters the thing. So clustering is a tool that's designed mostly for numeric predictors, because the categorical ones already kind of divide the data into clusters and groups, right? And so, but anyway, this is what we've got. Okay, so we'll talk about principal components analysis first, and that will probably be our first hour or so, and then we'll take a look at the clustering methods next, okay? And again, just kind of like everything else we've been doing in the class, a very high-level approach of just kind of sticking with the concepts and just the ideas of what we're trying to do, and there's and then we'll have, like, if we do it on the computer, we just have the computer do it. We don't do any of these calculations ourselves, okay? So okay, so we'll start with I guess this still talks about the challenge of unsupervised learning, but anyway, okay. Yeah, unsupervised learning, it's a little bit hard because we don't really, like, the idea of checking your work to see if you did a good job or not is it's hard to do when it's unsupervised, because there's no answers for you to check against, right? When you have a predictor variable and your goal is to predict some value, it's very easy to verify your work, because you can say, my model predicted this and I know the actual value is this, and you have a direct way to compare those two things, okay? That's for supervised learning. Unsupervised, you don't have that. You're just trying to say, well, did I do a good job of dividing the classroom into groups? I don't know. And it's difficult to evaluate. So that's one of the challenges we run into. Okay, principal components analysis, okay? We briefly touched on principal components regression. I don't even know if you can say we touched on it, okay? It just kind of went passing by in section chapter 6. But But the idea with principal components analysis is that we want to reduce the number of dimensions that appear in our data. So you might have high dimensional data, okay, and you want to kind of reduce the number of dimensions. And the way we do this is by creating something called a principal component, okay? A principal component is this, okay? This looks all funny, but it's basically a linear combination of your x variables, okay? It's just, and so for example, like one way to project your data, if you have 30 dimensions, okay, you could technically project it down to 2 dimensions, okay, very easily by saying, let's say you have your 30 dimensions for the football data, okay, so you've got x1, x2 up through x30, okay, and you can say, I just want to use the number of yards and, I don't know, the number of rushing attempts or something, okay? So then in that case, the principal component uses these values of phi here, okay? And we would give x1 for yards a 1, and then everything else gets a 0, okay? And so that weights all the 30 variables. It just basically says only this one is most important. And so basically z1 just reduces to x1, okay? And then if you wanted just rushing attempts, then you can, whatever variable, let's say x4 is the rushing attempts variable, okay? Then everything else would be a 0, and then phi 4 would be a 1, and everything else is 0, and that reduces the second principal component just to the rushing attempts. Is that okay? Should I write that down or? But generally, principal components analysis won't give you a 1 and 0. It'll usually weight these things and say, we're going to make basically some linear combination of these different predictors. We're going to say we want 20% of variable 1 and 30% of variable 2 and 2% of variable 3 and 0.0001 of variable 4 and so on and so forth. And it adds all of these up so that all of the phi's, when you square them, equal 1. So this is basically it's normalized, a normalized vector, so that it's, I guess, Euclidean magnitude is a unit vector, okay? And so we just have all of these kind of the loadings or the weights of each of these components to be normalized. But this says this is how we will weight the variables, okay? And by doing that, you can create new variables, some z1 or z2, that measures kind of similar features, okay? Similar values. And so I think when we talked about this a couple weeks ago in chapter 6, we were talking about predicting the price of a home, okay? And we said, when you're looking at the price of a home, there might be like 30 variables, okay? And some of those variables will be related to the size of the house, like the number of bedrooms, the number of bathrooms, the number of square feet, the size of the basement, things like that, okay? And in general, if you've got more bathrooms, you're going to have more bedrooms and you're going to have more square feet. And if you have fewer bedrooms, you're going to have fewer bathrooms and fewer square feet, okay? So all of those things kind of are related, and principal components analysis would probably put weights on those variables that are related, and everything else would get something very close to 0. And then another dimension of the house might be kind of the amenities and how nice it is. So it'll be things like the quality rating of the kitchen and the quality rating of the floors and the quality rating of I don't know, the roof and how recently it was built, okay? And in general, those things will be correlated, right? So if you have a nice kitchen, you'll probably also have nice floors and a nicer roof, and so those things will be correlated. And if the kitchen is kind of dumpy, then it's likely that the floors are kind of junky also, and I don't know, all sorts of other stuff, right? And so those things will be related, and the principal components will generally identify this and make these weights low, make the weights for those variables high and the other variables low, okay? And so the combination, the z, will represent something like the size of the house, and z2 will represent something like the quality of the house and things like that, okay? And that's what we get. And so when we do something like this, okay, we get some kind of linear combination here. This is how the way it's set up, okay? Don't worry about this at all, okay? It's basically, when it seeks out the loadings for the principal components, the goal is to maximize the amount of variance captured by the principal components. So after you make the loadings, it wants to capture the maximum amount of variance, okay? And so I'm going to come over to this website, which does a visual explanation of principal component analysis, okay? And so here we have two variables, okay, x and y, all right? And we can see that x and y are highly correlated, okay? So that as x gets bigger, y also happens to get bigger, okay? And so what the principal component analysis will do is we'll say, you know what? We can project this down to just basically one variable, okay? And it's going to be a linear combination of what x and y are, okay? And so we can see that when we project this data down, it ends up down to one variable. It looks like this, okay? And then it still projects it onto two things, but we could maintain something like this, okay? So, when you guys take, if you ever take the SAT or the GRE, they have different components of the exam, right? You've got the verbal and the math and the writing and things like that, right? And so some schools will say, we don't really only care about your math score. And others will say, we care about everything, or maybe just the sum. And they might want the individual components, your verbal and your math. And some might just want like a total score or something like that, okay? And basically the total score is kind of like a principal components thing where they're just asking, give me the verbal plus the math, okay? It's not normalized, okay? You've got a 1 over here and a 1 over here, so it's not normalized, but you're basically just combining the individual components into a single value, and they're using that, okay? And of course, when you have just one value versus two, you lose a little bit of information, because somebody who scored high on the math and low on the verbal might have the same total number as someone who scored high on the verbal and low on the math, okay? But maybe that distinction is not important, or maybe it is. Your GPA is also a linear combination of your grades, okay? It's not weighted, it's not normalized like a principal component, but it's also just a linear combination of everything, right? So if we took a list of all of your courses, I don't know how many courses you've taken, like 60 or something, you might have this 60-dimensional vector or something, and we just kind of combine them, right? We just say you're gonna weight each grade by this number, and each letter represents this number, and based on your credit hours, they get multiplied by something, and then we just add them up. It's just a linear combination of that, and this number, this whatever it is now a representation of your academic career. And so that's dimension reduction right there, okay? And so here, we just have two variables, x and y, and we can reduce it just to one, okay? And we can see this value right here shows up as, I guess, around a +4, and this value down here shows up around -3, okay? And here's the neat thing, is I can drag this thing, and we can see how it moves the diagram, right? And so if I move everything kind of like this, all right? So now the principal component, okay, if I line them up this way, now the principal component looks like this, and it looks like this is what it ends up looking like, okay? And I can kind of move things around. And basically, it's just trying to find a projection of this, okay? And it says, here's the principal component's direction. This is the direction that maximizes the variance, okay? And of course, if we look only at principal component 1, it just lines up along the zeros, okay? But this is what we would end up getting, okay? So you can kind of just move things around. And what the PCA is trying to do is it's trying to find the direction along which the maximum amount of variance is captured. Okay. So this is kind of silly because we're projecting from 2 dimensions. Over here it's 2 dimensions down to 2 dimensions over here, except we've done it in such a way that preserves the first principal component and the second principal component are horizontal and vertical. Okay. Okay. So in this case, the most amount of variance is captured vertically, and it appears like this. Okay, and so here, yeah. So this is a good visualization. In the x and the y, this is what it looks like when you project it onto the first principal component. This is how they get projected. Okay, if I move things around like this, okay. There's a lot of variance in x and a lot of variance in y. By projecting it, okay, we maximize the amount of variance captured in principal component 1, okay? So you can just see these are just the dots kind of projected down, okay, onto one dimension. And then in the second, we have a lot less variance here. Okay. So anyway, this is a fun little website that you can kind of mess around with. And I don't know, I think, okay, so here we've got a lot of variation in x and y, but when we project it down, we have maximized the variation in this, and consequently that will reduce the amount of variation in the second principal component, because the second principal component is always orthogonal to the first principal component. And so if we were to suddenly just delete principal component 2, we still maintain a lot of the information captured in this data. Okay, we maintain a lot of variation that exists in the data. So the point of a goal of principal component analysis is that we can perform data reduction or dimension reduction. And so here we have 2-dimensional data, and we redo it to 2-dimensional data, but we see that the second dimension, PC2, doesn't contain that much information, and so if I get rid of it, we're not losing too much. Okay. All right, and then so similarly, we can do it in 3D, okay? And so here is the data plotted in 3D, and this is currently how it appears, and you can change how the orientation of kind of these directions here. All right, and the goal is to maximize the amount of variation captured in principal component 1. Okay, so when we project it in 3D, we can see that there is kind of like 3 distinct clusters. Okay, but if we can't, those 3 clusters are not really pronounced here. Okay, and if I do this, certainly this would be a bad projection, because under the first principal component, it just looks like a blob here, right? And currently under X, Y, and Z, you can't tell that there's 3 components, but if you find the correct analysis, you might be able to identify 3 structures here, okay? And so if I click Show PCA, it's going to find the structure here, and we can see in the first principal component there indeed is, we can identify kind of 3 clusters here, okay? And so principal components analysis is useful for identifying kind of the underlying structure in our data, okay? And if we were to drop PC3 or even PC2, we would lose some information, okay? But we still have maintained and captured a great amount of the variation. Whereas in the original projection of the data, the X, Y, and Z, that clustering nature where there's 3 clusters, it isn't seen here, okay, in X, Y, or Z. And therefore, dropping any one of those variables might cause us to lose significant amount of information, okay? And so we could imagine something like this applying to a very high-dimensional data set, okay, a very high-dimensional data set, and principal components analysis will help us to identify clusters or structure within the data, and allow us to kind of visualize it in a lower dimensional setting, okay? So here's another case where we've got 17 dimensions, okay? So this is food eaten in the United Kingdom, okay? And so the United Kingdom, we always just kind of refer to it as Britain, but in Britain, it's actually United Kingdom of Great Britain, which is the kind of the big triangle island, plus Northern Ireland, and it's complicated. Ireland is split into 2 parts, and I guess there's 4 countries within. So we have England, Northern Ireland, Scotland, and Wales. And okay, and so here we have 17 dimensions, and we asked, how much alcohol do you drink? Okay, and in England, they said this much, and in Northern Ireland, you drink this much and stuff. And then we say, how much fish and fresh food and fresh vegetables and stuff do you eat? Okay, and the question is can we identify something? Okay, and so when we do principal component analysis, okay, what ends up happening is that Northern Ireland ends up way over here, and Wales, England, and Scotland end up over here. And so we want to know, well, kind of like, so what this is basically saying is that the countries on the island of Great Britain, okay, Wales, England, and Scotland, are more similar, and Northern Ireland, which is on its own separate island, is quite dissimilar. It's quite different from the others, okay? And it might not be so obvious when the data is presented like this. So you can take a look at how this ends up being, and a closer inspection of the data shows something interesting. Okay, so one thing is alcoholic drinks. Northern Ireland consumes much less than England, Scotland, and Wales. Okay, and we'll also notice, look at the difference between fresh fruit and fresh potatoes. Okay, so fresh fruit in England, Scotland, and Wales, they all consume more fruit than potatoes. Okay, but in Northern Ireland, they consume less fresh fruit than potatoes. It's the only place where they consume more fresh potatoes than they do fresh fruit. Okay, and apparently this distinction, as far as soft drinks and processed vegetables and stuff, they all kind of have similar shapes, right? They have they all look like this. But look at fresh fruit and fresh potatoes. We see that Northern Ireland consumes a lot more potatoes and a lot less fresh fruit, whereas the other places they consume more fresh fruit and fewer fresh potatoes. And principal components analysis will identify kind of this kind of variation and allow us to kind of project project this onto here. Okay. Now, unfortunately, you don't get insightful names. Okay, you just get PC1 and PC2, and so it would depend on the kind of person doing the analysis to look at the data to kind of see if there's something that they can gain insight from, because the principal components analysis is just going to apply the algorithm which says let's find a linear combination that will maximize the variance once we project it down. Okay. Okay, so anyway, that's what all this stuff says, and they use a rather grim data set on U.S. arrests using violent crime, okay, murder, assault, and rape, and they're looking at urban population, and they've got data on however many cities, okay. And this picture is called a biplot, okay? And we have the first principal component, okay? And so if you look at the first principal component, it puts a high ranking on murder, assault, and rape, okay? And fairly low weighting or low loading on urban population, okay? And according to the first principal component, Florida, Nevada, and California are all high, and South Dakota, Vermont, and New Hampshire all rate low. Okay, and so, whenever this data was collected, this indicates that California, Nevada, and Florida had high numbers of murder, assault, and rape, and therefore they are similar in regard to the first principal component. So these arrows represent basically the weighting, and so we can see that these three, as far as the first principal component goes, are all rather similar. If we look at this dot and these are the weightings, so these are similar and gets a low weighting in the urban population. Is that okay for the first principal component? And then the second principal component puts a very high weight on urban population, and a comparatively much lower weight on the violent crimes. Okay, and so basically what we have here is then California, Hawaii, Rhode Island, New Jersey are similar with regards to the second principal component. These would indicate that these states, California, Hawaii, Rhode Island, New Jersey, have a high urban population, which makes sense. The population of Rhode Island is primarily urban. It's such a small state, and pretty much everybody who lives in Rhode Island lives in a fairly urban center. Similar for California, most of California's residents live in the urban parts of California, whereas North Carolina, Mississippi, South Carolina apparently have lower urban populations, and whatever combination of murder, assault, and rape and stuff like that, they rank lower here. Okay, it's not the most fun data set. It's kind of, yes, question.
So the way you're interpreting the first principal component is if they line up on that axis, they have just something in common.
They have similar weightings. Okay, so remember, these arrows are a reflection of basically the 5 values that are used to kind of combine these things. So for example, if I were to just, let's say we did house prices, okay? Not even housing prices, but we did the housing, right? And our variables are things like square foot, number of bedrooms, bathrooms, okay? And then I'll do kitchen quality and floor quality. I don't know what bathroom quality or things like this, right? So if we were to make a biplot, what it would probably look like, okay, so we'd have PC1 and PC2. I imagine, and I'm just making this up completely, okay? I haven't actually done the principal components analysis, so don't get mad at me. I imagine one of them will have something, I'm just trying to think, square footage, bedrooms, bathrooms, there's something that's going to be negatively associated, okay? Something like this, kitchen quality, floor quality, bathroom quality. Okay, maybe I will also do year built, okay? All right, so I think this will be something like square foot, and maybe bathroom and kitchen, okay? And then PC2 might look something like this. So this will be year built, and this will be kitchen and floor and bathroom or something like that, okay? And basically what this is saying is that PC1 is basically size, okay? So basically high values correspond to large home, and lower values correspond to a small home, okay? And then PC2 will be something like quality, okay? So high values will indicate like I guess year built, maybe not year built. We'll do age of house. Sorry. It's just the opposite. Okay. Okay, and then so high values indicate something like nice modern homes, and then low values will be like old and dilapidated. Okay, and so kitchen, floor, and bathroom quality, we would expect high ratings. Like if you rate this on a scale of 1 to 5 or something like that, then the homes that have 5s for the kitchen, floor, and bath will generally be associated with high quality and stuff like that. And probably the age of the house will be will have lower is better, right? So age 0 and 1 will probably be nicer, whereas like if the age is 40 years old and I don't know, hasn't been aged since the last renovation or something, the kitchen, floor, and bath will also be lower or something like that, okay? Does this kind of make sense as far as how the arrows are working? Okay, so these indicate that, and again, I'm just making this up, all right? The analysis will not label PC1 as size and PC2 as quality, okay? It just says this is how we've captured the most amount of variation in our data. And this is, and then so a home, so if we have a data point right over here, this would be a big house that looks very new, okay? So this is the big and nice house, okay? Here is like big but falling apart, okay? And this over here would be small but very nice. And this is small and falling apart. Right? So this would indicate something that has low scores on kitchen, floor, and bath, and high score on age, or something like that. Yes?
So there are two baths here. So one is faulty and one is faulty, or
What's that?
there are one bath near the PC one.
Oh, yeah. Okay, yeah. So this is, sorry. Okay, so this is bath size, or bath number. Oh, and this is not kitchen. This is bedroom number. And then these are bath quality, floor quality, and kitchen quality, okay? Indicating like how nice the kitchen is or something like that. Okay, does that kind of make sense what this biplot represents? All right, and so again, this is just a way to reduce the number of dimensions that we have down to something that's a little bit easier to plot and visualize, okay? If we wanted to try to plot all of the variables for the house, it wouldn't be possible to do, right? But if we do some kind of principal components analysis or something, we can kind of plot this, okay? Now, you can kind of manually do this, and you can just say, you know what, like without normalizing the variables, you can just say like, I've come up with this way of creating a measure, giving, I'm gonna give a house a size score, okay? Which will be the, we're gonna take the square footage and we're gonna add, 0.2 of the lot size and multiply the bedroom number by this and this. Like you can come up with some arbitrary scoring metric for square footage or something like that, okay? It doesn't necessarily have to do this. Okay, so an interesting application of principal components analysis, and it's not covered in our textbook, but basically, all right. Okay, I'll tell you, it's in the Olympics. Can you guys think of where the Olympics could employ PCA? Okay, Olympics, it's going to be Olympics track and field. Okay, and it's going to be the multi-event, or I don't know how you call this, the multi-event competitions. Things like the decathlon or the heptathlon, okay? So in track and field, you can participate in something called the heptathlon, right? And in the heptathlon, there are 7 individual kind of events, all right? I don't know. So I think there's 7 events. Things like how fast you, like, I don't even know what they are. Olympic heptathlon. Okay, let's see. So okay, so you got 100-meter hurdles, high jump, shot put, 200 meters, long jump, javelin throw, and 800 meters, okay? So you have all of these things. You have to like run, and you have to jump, and you have to throw things, right? And this takes place over a couple days, right? And so so you do this. Now, it's not there's only one gold medalist, right? Okay, so how do we pick who gets the gold medal? Like somebody, let's say this person was really fast at running, so they got the 200 meters and the 800 meters. They were really good. But what if they did terrible? Like their arms are weak, and so they can't really throw the ball very far or the javelin very well, right? So like let's say I don't know. Okay, I'm just making this up, right? How does that rank with somebody who maybe they didn't win all the running races, maybe they came in second place, but they also threw the javelin really far and stuff like that? Okay, how do we come up with some system for doing this? Okay, well, for the heptathlon, is they use some kind of points system. Okay, and they came up with these kind of arbitrary numbers and stuff. Well, not arbitrary, but they seem like random. Like, how did you come up with these numbers and stuff? Okay, but basically, it's kind of an application of principal components analysis in that we wanted to find a way to reduce the number of dimensions from 7 dimensions down to 1 dimension where we can rank them and say this was the best and this was the worst. Okay, and so something like this, 7 events. Okay, and this gets reduced to 1 dimension to produce a single ranking list from gold to silver to last place. Okay, and so that's kind of a interesting analysis of our application PCA, and so after kind of looking at the things, they have these scoring systems with these points and say, the way we give you points is you're going to take your 200 meter score and subtract off 42.5, or take 42.5 seconds, subtract off your time, raise it to the 1.81 power, and multiply it by 4.99087. Okay, it seems a little bit arbitrary, but basically, if you follow this thing and do the point system and you use PCA, generally the scorings will the results will line up quite closely. Okay. So anyway, so that's a dimension reduction thing here. Okay. Okay. So yeah, here's just another thing where you have 3-dimensional data, and we kind of saw something like this with the website, or the 3-dimensional data. They applied principal components analysis, and they projected it down into 2 dimensions, and then they were able to do some kind of thing to group them together. Okay. Some important things is that because you're trying to maximize variance, there's it makes a big difference on whether you choose to scale the variables or not. Okay, so if for something like the heptathlon, obviously the 800 meters run is going to take a lot longer than the 200 meters run, right? And so do you just treat the time differences in 200 meters and 800 meters the same, or do you so if somebody beat another person by 1 second in the 200 meters, and another person beats somebody else by 1 second in the 800 meters, should that 1 second difference be treated the same? Probably not, right? In the 800 meter, the 1 second difference is a lot less than the 1 second difference in the 200 meters, right? And so that would be a case where you'd probably want to scale the results. Similar for the javelin throw and the high jump and the long jump, right? The long jump, like the difference between one high jump and another high jump is going to be very small, like just a few centimeters of difference between the winning and the losing high jump, right? They make tiny increments, okay? But the long jump, you can cover a lot. Yeah, I mean, it's also going to be a small difference at the Olympic levels, but as far as it's a lot easier to jump the length than it is to fight gravity and jump high. So oftentimes we will apply scaling for these things, okay? But in some cases, you might not want to scale the variables, and this is always a question, and the answer is always it depends, depending on the situation. So scaling the variables does make a difference on principal components analysis. And so that's just something to keep in mind. If you if you scale them, you get quite different results. This is scaled, which is generally scaling is recommended for most but not all situations, okay? And if you do it unscaled, you get very different answers. All right. And so in this case, what we see here, okay, is that the assault gets rated a lot higher because there's just generally a lot more assaults than there are murders, okay? So assault is anytime somebody that punches somebody, okay, then that's an assault. And so there's a lot more, not that we should be proud of any of these things, but there's just a lot more physical violence that does not result in someone's death than people murdering another person. And so this ranks treats the assault as much more weighted heavily to capture kind of more variation as far as that goes, okay? And so that appears there. Principal components, two people can do the same principal component analysis, and they can get the same results except for the sign. The sign of what is positive and what is negative is arbitrary, and so in these diagrams, you can have another result where you just get the negative of another thing, okay? And so you'll get the same results, but just the negative, okay? So the sign flip is just something to be aware of, okay? And then as far as when you do the dimension reduction, you can ask kind of the proportion of variance that is kept, or a proportion of variance explained by the different principal components. And so if you have 17 dimensions in your original data, to capture all of the variance that exists in the original data, you would also need 17 principal components, okay? But chances are is that even if you keep only the first 3 principal components, you will end up capturing something like 90% of the variation. I'm just making those numbers up, but that means you can reduce from 17 dimensions down to 3 dimensions, 3 principal components, and lose only about 10% of the variation that exists in the data, okay? And so generally in R, when you perform principal components analysis, there will be, you can create a plot or a listing of how much variance is kept by each principal component, and you can make a decision. So you can get a plot like this, and this says, if you keep only one principal component, you get about 60% of the variation. If you have 2 principal components, you get about, looks like 85%, 80-something percent. And with 3 principal components, you get almost 100%, okay? You lose just a tiny bit, okay? And if you keep all 4 principal components, you'll get 100% of the variation. And so a graph like this can kind of give you an idea of like how many principal components you should keep. And again, this is just another judgment call on, you know, at what point is the gains not worth it. Probably, I would say keep 2 principal components, and you can ignore the last 2. But people might have different opinions there. Okay, how many principal components to use? Yeah, you can make this thing. They call this a scree plot. We don't have. There's no cross-validation to use for principal components analysis, okay? Because there's no way to like check. There's no answers to check against, right? To do cross-validation, you need to have the right answers. You need to have a y variable to predict, and you take your predictions and you compare them against that, okay? That doesn't exist for principal components analysis. And so, so it's not the easiest thing to do, okay? Okay, we'll take a break here. I guess we'll say 5 minutes or so, and then we'll take a look at the clustering examples to wrap up chapter 10. Continue on. All right, I think this is good. Okay, so the other part. Oh man, it's already 1:30. Okay, clustering methods. Okay, so clustering methods. We're just trying to find subgroups or clusters in a data set. This is a very difficult thing to do because you're just trying to group observations together using some arbitrary measure of similarity. Okay, and again, clustering almost always used for numeric variables, okay? It's very difficult to do clustering with categorical variables. That's not to say it doesn't exist, okay? People have tried to come up with ways to cluster based on categorical variables, but it's just, like if I have 2 variables and it's like gender, male or female, and I don't know, major, North Campus or South Campus major, right? STEM or non-STEM major. Then naturally, you're going to have 4 clusters, you know, males who are STEM, males who are non-STEM, females who are STEM, females who are non-STEM, right? It's naturally going to form kind of 4 clusters that way. So how do you perform cluster analysis beyond that? It doesn't exist, or I mean, it doesn't work super well, okay? And then I guess, you know, if you have throw in another variable that's numeric, then it raises a whole bunch of questions, right? Like, what's more important, that you know, is it more important that the sex is similar, that we cluster on sex, or is it more important that we cluster on major? And these are just questions that are very difficult to answer. So clustering is very hard to do with categorical variables, okay? But if you've got numeric variables, then we've got an assortment of things, methods, and a lot of it comes down to how do you measure what is similar versus what is different, right? And so the simplest is to use something like Euclidean distance. You just take your x variables and you kind of plot them, and you just take the difference between them and you square them and you add them up, okay? And then I guess you square root all of that. So you can use Euclidean distance as a way to measure similarity or something that's different, and that's what k-means clustering does, okay? So in k-means clustering, it writes a whole bunch of stuff. But basically, it's going to use Euclidean distance as a measure of what is similar and what is different, okay? And it takes the points and it kind of assigns them to a cluster, and what it will do is it will find the center of the cluster and then reassign all the points to that thing. I've got some slides from 102B that cover this, and I'm just going to show them here briefly. And then if you do take 102B, you'll see these again. If you've already taken 102B, then sorry, you get to see these slides again. Okay, so here there's two natural clusters in the data, and so the way it works is you just arbitrarily sum to red and sum to blue, and I don't know if you guys can see the colors, but these three up here are red, and these two down here are red, and these two are black, and this one is black, okay? And then what it does next is it calculates the mean of the red points and the mean of the black points, and this is the mean of the red points and the mean of the black points, okay? The centroid of the red points and the centroid of the black points. And then it just says, okay, now that here's the centroid of the red and here's the centroid of the black, reassign all the points to the cluster that's closest using the Euclidean distance. So you just measure the Euclidean distance from each point to each cluster, and you say, okay, well, this point is closer to this centroid than it is to this one, so this point will get assigned to the red cluster. This point is closer to this centroid than it is to that one, so it's going to get assigned to the black cluster. And so you do that, so it goes through and it compares the distance, and it says, all right, so these get assigned to red and black, and then you recalculate the centroids, and then no assignments get redone. Okay, here here's just some arbitrary data where let me just dim the lights a little bit. So here, some points are red. Wait. Okay. I don't know what just happened, but all right. My desk is super bright. But okay, we just randomly assign some to red, black, and green, and we calculate the centroid of all the red points, the centroid of all the green points, and the centroid of all the black points. And so they get assigned this way. And then we go for each point and we say, all right, which centroid is the closest, okay? And so basically for all the points over here, the green one is going to be the closest. For everything over here, the black centroid is the closest. And then for some of these points, okay, like this point is probably closer to red, and this point's probably closer to black, and so we're going to get kind of a boundary between red and black here, and then we might get a boundary right here between red and green, okay? And so after we do the reassignments, this is what happens. These are all green, these are all black, and just a few of these are red, and we just recalculate the centroids again, and so they go there, and then we say, okay, now we're going to reassign points, okay? And so this point, which is currently assigned to black, is probably closer to red than it is to black, and so this will get assigned to red. And then this point, which is currently assigned to green, is closer to red than it is to the green centroid, so these ones in the middle will get reassigned. So we do that, and this is the reassignments. We recalculate the centroids. Okay, the centroid of the black points is now going to be over here, and the centroid of the green points will now move over here. So we recalculate the centroids, we reassign points, recalculate the centroids, and we just keep doing that until there's no more changes and this has converged, okay? All right, and so anyway, this is what it does. The issue with k-means clustering, though, well, I don't know about the issue, okay? Just one thing to be aware of is that it uses Euclidean distance to measure similarity, which may or may not be the best measure of similarity, okay? And the other issue is how many clusters we use is difficult to decide, okay? And we don't have a clear answer for how many clusters we should use, right? So for example, and this is always an issue, right? Like how many, it's as difficult to answer as trying to answer the question, how many different races or ethnicities are there? Okay, and you might just say, okay, well, there's only one race, the human race. Correct answer. Okay, that's fine. Okay, you can also say, in a lot of America historically was either you were white or you weren't white. Okay, and everyone who wasn't white was kind of classified as not white, and that was how it was historically, and then probably today we would recognize, I don't however, you can have white and black and Asian and Hispanic and further, you could further subdivide any of these things, right? So as far as Asian goes, that can further be divided into like South Asian and East Asian and Southeast Asian, and then you can further divide any of those things, right? You can further divide East Asian into Chinese, Korean, Japanese, and then you can further divide Chinese into whatever, and the question is, how many clusters do we need? And it's not an easy question to answer, right? Like, when do we stop dividing and saying, okay, this is the correct number of clusters, we've captured everything that we should? And so, if you just think, and I, as far as the racial ethnic categories go, I think we recognize the difficulty in deciding how many categories are necessary. It's a very difficult question to answer. This is like when the US Census tries to print out the thing where people fill out the forms, they're always not sure how to do this. And then, and things get complicated, right? Because a lot of people are also mixed race, where they are combinations of multiple ethnicities and stuff. And how does that work? So picking the number of clusters is hard. And, here it's abstract. And we go, oh, is this good? Yellow and blue, or green, yellow, and blue? Or do we throw, I don't know, okay? So this is a difficult thing to answer. There you have a measure that talks about kind of the distance from each point to the center and the total kind of cluster difference, okay? And so there's, these are a few tools, and basically the more clusters you add, this distance, total distance to the centroid, gets smaller and smaller, okay? And so you have a few, you can kind of create a plot to see if adding an additional cluster reduces the, whatever this quantity we call, okay? The total, total squared distance to the centroids. These are just the diagrams of the clustering solutions, and I don't know. So for us, R does k-means clustering very easily. You just call k-means, and it will give you the answers. It does a few things. When you call k-means in R, it often starts with different random seeds. And because depending on the random configuration you have in the beginning, you can end up with different results, okay? So depending on the random configuration, it might converge to different things, okay? So these are just, so this is one result, and it converged to a, less optimal solution. And these four converge to kind of the optimal solution, it seems, with 3 clusters. And this one also converged to a less optimal one. And so R will perform kind of several threads of k-means clustering and give you the one where it found the optimal solution most of the time, okay? Which is nice, okay? So the algorithm written in R for k-means clustering is pretty good, but again, choosing how many clusters, that's just something we're not really able to answer easily, okay? Again, when you figure out how many ethnicities there are, then you know it's as difficult of a question as that. Picking how many clusters there should be. I mean, in some cases it's very clear and easy, but it's not always the case, and more often than not it's hard. Okay. Okay, and then the last method is hierarchical clustering. Okay, it sounds fancy, but like a lot of other things, they're simple. Okay, so the hierarchical clustering produces something called a dendrogram. Okay, and they look fancy. Okay, they look like these things. Okay, this is the result of hierarchical clustering. But let me just kind of skip ahead to it. Okay, basically it starts off here, and it starts off with each individual point as its individual cluster, right? And what it does next is it goes through, and so in this case we're using Euclidean distance to measure similarity, okay? But again, there are other measures for similarity, but Euclidean distance seems to be kind of the easiest to use. And so anyway, we start off with all the points as individual clusters, okay? And then we say which points are the most similar, okay? And we go, okay, so we look at every possible pair of points and we go, oh, 5 and 7, those are very similar. They have a small distance between them, okay? So these 2 points get clustered together, okay? And then we go, okay, well, which points are the next similar? Okay, and then so these 2, 6 and 1, are clustered together, okay? And as we go, all right, what next set of points? And it turns out that if you look at the center of 5 and 7, okay, the center of 5 and 7, because now that we've clustered them together, they're going to get represented by the center. The center of 5 and 7 to 8 is the next closest kind of distance here, okay? And it further continues up to form this dendrogram, okay? So we get the 1 and the 6 are similar, and then the 5 and the 7 are similar. The 5 and the 7 are the most similar, and then between the 5 and 7, the 8 is the next most similar thing, okay? And then the next thing will be the 1 and the 6 is close to the 4, and then the center of these things is close to the 3, 1, 6, 4, and the center of those things is close to the 3, and then the 5, 7, and the 8. The center of that is right here, and the next closest is the 2, and then the center of those, the next closest is the 9, okay? And then finally, they get clustered together there, okay? So one thing to watch out for, though, is that you have to look at for this dendrogram, you have to look at the vertical distance, not the horizontal. So here, like the 8 and the 2 look like they might be similar because they're like kind of next to each other, but they're not, right? They're quite different. And you have to kind of look at, all right, the merging of the 5, 7 and the 8 together along with the 2, this is kind of this vertical distance here represents the similarity or the dissimilarity there, okay? And so that's what that's what happens, okay? And so when you apply it to a big data set like this, okay, you can get all of these results. And so there's 45, I think, dots in the plot, and so they all get represented here, and so it clusters them again the same way. It just kind of says like, okay, these 2 points are really similar, and these 2 points are really similar, and these 2 points are really similar, and it clusters them together, and then it kind of groups them, right? And you can use like an arbitrary cutting point, and if you do an arbitrary cutting point here, it's going to end up creating on this branch everything that's green, and on this branch everything is purple, okay? Or you can cut it here and it will produce 1, 2, 3 clusters, and it will say these green are similar, and then everything down this thing is yellow and everything down here is purple, and that's what this plot represents. These are the yellow, these are the purple, and these are the green, okay? And so this is the result of the dendrogram. So the dendrogram starts off at the bottom. Everybody is individual, and it says which two are the most similar, in this case using Euclidean distance to do that, and it builds it up that way. And so once it kind of groups them together, it's like 1 point there, and until it all kind of clusters into one centroid at the end. Is that all right? So as far as the hierarchical clustering and the dendrograms, they sound a lot, I think a lot fancier than that. Okay, so here is how we kind of group things together. All right. So I think the other ones were so far we did the centroid. Okay, dissimilarity between the centroid for cluster A, the mean, and the centroid for cluster B. But you can do something like the linkage is the complete maximal intercluster dissimilarity. Compute all pairwise dissimilarities between the observations in cluster A and the observation in cluster B, and record the largest of these dissimilarities. So rather than just kind of using, the center of this cluster and the center of this cluster and measuring how similar, dissimilar they are, you can look at every single individual thing over here and compute every single thing over here and compute them that way. So there's different ways in terms of how things should be linked up, and so yeah, the choice of dissimilarity measure. So far we've used Euclidean distance, but there's other things like correlation-based distances, and different options here. Oh, I forgot. Okay, so yeah, here it talks about an example where you're trying to cluster shoppers that are similar, okay? And so they are kind of looking at, a matrix where the columns are the items for purchase, and then and here it says if you use Euclidean distance, okay, then the shoppers that have very few items overall will end up being clustered together, okay, which is probably not what we want, okay? And here we have correlation-based distances, okay? And in that case, it says shoppers who've bought item A and B, but never item C and D will be clustered together, even if they have different kind of volume measures. So again, just different ways of measuring similarity. So correlation is another choice. Euclidean distance is probably the easiest to visualize and picture in our head, but there are other kind of distance metrics that we can use. Okay, and so this is just kind of more examples of the correlation-based clustering there. Okay, I think that's about it. These are always some considerations, like do we scale things or standardize them? These are hard questions to answer. How do we measure what's similar and what's different, right? Euclidean or something else, and do we use the centroids or do we use something else to kind of link things together when you're doing hierarchical clustering? And how many clusters should we search for? There aren't clear-cut answers for any of these things. A lot of them require a little bit more understanding of the data rather than just blindly throwing things at the machine, okay? But these are all part of your toolkit and things that you can try and explore and see if they're helpful in identifying structure. And what happens will always vary a little bit. Okay, I'll create a homework assignment covering chapters 9 and 10, and then and I guess that will be it. Four homework assignments, and we'll see you guys on Wednesday. I'll try to think of something at least fun or interesting, in my opinion, and we'll go from there. So, okay, and today will be your last discussion section with the TA. She'll cover the labs in chapter 10, which I always think the practical applied part labs are helpful as well. So stick around for that, and we'll see you guys on Wednesday.